Here are a few questions from the paper Classical Mechanics. We will go through them one by one. First question is, what is meant by degrees of freedom? The minimum number of independent coordinates required to describe the motion of a particle is called degrees of freedom. The degrees of freedom is given by the formula F is equal to n into d minus k. Here d stands for the dimension. N is the number of particles. K constraints imposed. If you go through this example, you may get an idea. Consider a particle moving in three-dimensional space along the x direction. Find the degrees of freedom. Now we have to draw a three-dimensional space. This is three-dimensional space x, y, z. Here the number of particles n equal to 1. The particle is moving along the x direction. Say the motion of the particle is along this direction alone. There is no motion along y and z direction. Therefore, the constraint k equal to 2. Total number of coordinates present is 3, but the particle is eligible to move along the x direction alone. So the remaining two directions are constrained, not allowed. Therefore, k equal to 2. Then the dimension is 3. The total dimension present here is x, y, z. Therefore, the degrees of freedom F is equal to n. Only one particle is present, so n equal to 1. Then the value of d, dimension is 3 minus k value, constraint value is 2. Therefore, the degrees of freedom is 1. Now read out this statement. The minimum number of independent coordinates required to describe the motion of a particle is called degrees of freedom. Even though 3 coordinates are existing, the particle is moving along the x direction alone. If you know the value of x, we may specify the position of the particle after a certain interval of time. Second question is, what are constraints? The geometrical restrictions imposed on the motion of the particle are called constraints. For example, in a simple pendulum, the length of the wire is fixed. Say, this is a simple pendulum. A ball attached at the end of the string will constitute a simple pendulum. Here this length is fixed, which will restrict the pendulum's motion beyond certain distance. Only with the help of this length, the pendulum is making its displacement to certain extent. Here the constraint is the length of the pendulum. Now read out this. The geometrical restrictions imposed on the motion of a particle are called constraints. We may classify the constraints into different types: holonomic, non-holonomic, sclerodynamic, and so on. Question number 3 is, what are holonomic constraints? If the constraints of a system are expressed in an equation of the following form, that is f of r1, r2, r3, rn, t equal to 0, such constraints are called holonomic constraints. Here r1, r2, r3 are position coordinates. The constraints imposed on a system are expressed in an equation of this form. Such constraints are called holonomic constraints. Example for holonomic constraints include: a particle is freely moving on a circumference of a circle. Only one coordinate is needed to describe particle's motion since the radius is a constant. Suppose a particle is moving in a circular path then the motion of the particle is described with the help of a single quantity. Say r is equal to a. R minus a equal to 0. See this, we have had an equation of this form. So this is example for holonomic constraint. Constraints involved in the motion of the point mass of a simple pendulum are holonomic. The constraints involved in the motion of rigid bodies are holonomic. These are all the examples of holonomic constraints. What are non-holonomic constraints? The constraints which is satisfy the inequality equation are called non-holonomic constraints. In the case of holonomic constraints, we are having this function equal to 0, but here we are having inequality symbol equal to 0 or greater than 0. Say r square minus a square greater than or equal to 0. This is an inequality equation. Suppose constraints which are satisfying the equation of this type are called non-holonomic. The constraints involved in the particle's motion placed on the surface of a solid sphere are non-holonomic. The constraints involved in the motion of the molecules in a gas container are non-holonomic. These are all the examples of non-holonomic constraint. Suppose the constraints are expressed in the equation of this form equal to 0, such constraints are holonomic. Equation may be 0 or may not be 0. That means inequality. Such constraints are called non-holonomic. Then question number 5. What are sclerodynamic and rheonomic constraints? If the constraints are independent of time, they are termed as sclerodynamic. You know that scalar constant is independent of time. If the constraints are independent of time, they are called sclerodynamic. If the constraints have time explicitity, they are called rheonomic. The time is exposed in a constraint. Such constraint is called rheonomic. Question number 6. What are generalized coordinates? For a three-dimensional system of n particles, a number of particles are present in a three-dimensional system x, y, z. We need 3n minus k coordinates to describe the system. Suppose n particles are moving in a three-dimensional system, the degrees of freedom f is equal to 3n minus k. For a three-dimensional system of n particles, we need 3n minus k coordinates to describe the system. If these coordinates, Cartesian coordinates, are replaced by the variables q1, q2, q3, q3n minus k and are called generalized coordinates. Instead of x, y, z, we may use q1, q2, q3 and q3n minus k coordinates. Such coordinates are called generalized coordinates. Question number 7. Define the term generalized momentum. Consider a particle of mass moving along the x-axis. Its linear momentum p equal to mx dot. We know that p equal to mv, but v equal to x single dot. Single dot means dx by dt. And the kinetic energy is half mv square, which means that half m x dot square. Differentiating t with respect to x dot. If we differentiate this equation with respect to x dot, we can get dou t by dou x dot. Dou t by dou x dot, which is equal to 1 by 2 into 2mx dot, then dou x dot by dou x dot 1, which is equal to mx dot. X dot is our v. This is m into v, which is our p. Therefore, p equal to dou t by dou x dot. We know the Lagrangian equation. L equal to t minus v. but potential is independent of x dot. V is free from x dot. That means V is free from velocity. Potential is free from x dot. Instead of this T, we can use L. Actually, this is dou by dou x dot of T minus V. But dou V by dou x dot equal to 0. Therefore, we can write this one as dou T by dou x dot. Dou V by dou x dot equal to 0. Then P equal to dou T by dou x dot, which is equal to dou L by dou x dot. In this way, we have arrived at this relation. For a system described by a set of generalized coordinates q1, q2, q3, qn, we defined generalized momentum pi corresponding to generalized coordinate qi as. Here replace this x dot by q dot. Then generalized momentum pi equal to dou t divided by dou qi dot. Here we have to replace these Cartesian coordinates x dot by q dot because q is a generalized coordinate. If you study the value of ith component momentum pi, which is equal to dou L divided by dou qi dot. This is our generalized momentum. Eighth question is, what are cyclic or ignorable coordinates? Coordinates that do not appear explicitly in the Lagrangian of a system are said to be cyclic or ignorable. Certain coordinates are not appearing directly in the Lagrangian equation. Such coordinates are called cyclic or ignorable coordinates. If qj is cyclic, then dou L by dou qj equal to 0. We know the Lagrangian equation d by dt of dou L by dou qj dot minus dou L by dou qj equal to 0. This is our Lagrangian equation. See, if qj is cyclic, then the value of dou L by dou qj is 0, which means that the second quantity is 0. The above equation is reduced as d by dt of dou L by dou qj dot equal to 0. Therefore, dou L by dou qj dot equal to constant, because if you differentiate a constant, we can get 0. This is our generalized momentum Pj. So Pj equal to constant. The generalized momentum conjugate to cyclic coordinate is conserved during the motion. Therefore, the coordinates that do not appear explicitly in the Lagrangian of a system are said to be cyclic or ignorable. Suppose that coordinates are not appear directly in the Lagrangian, then dou L by dou qj equal to 0 if qj is cyclic. State the principle of virtual work. In a n-particle system, the total work done by the external forces when virtual displacements are made is called the virtual work, and the total work done is 0. You know that work done is force into distance moved. If you are trying to move a substance of greater mass, even though you are providing your contribution to shift the body from this place to some other, it is not possible for us because of the huge mass. Anyway, we have taken much more efforts. But work done is actually 0, but the displacement is infinitesimal, very minimum, not predicted. Therefore, Fi dot del Ri, work done is equal to force into distance moved, equal to 0. This is called principle of virtual work. Work done is not real, it is virtual. In state D'Alembert's principle, consider the motion of an n particle system. Let the force acting on the ith particle be Fi. By Newton, force acting on a body is equal to rate of change of momentum, that is d by dt of mv. Actually, force acting on a body is directly proportional to rate of change of momentum. To remove the proportional design, you have to introduce a constant. Such a constant value is 1. So F is equal to d by dt of mv. This is equal to d by dt of pi, momentum acting on the momentum of the ith particle. Rate of change of momentum of the ith particle is pi dot. Therefore, Fi equal to pi dot. Then Fi minus pi dot equal to 0. Consider the motion of an n particle system. Let the force acting on the ith particle be F suffix I. By Newton's law, Fi equal to pi dot. We have proved this. Fi equal to pi dot. Therefore, Fi minus pi dot is equal to 0. This means that the ith particle in the system will be in equilibrium under a force equal to actual force plus reversed effective force minus pi dot, as named by D'Alembert. This is Fi plus minus pi dot, that is equal to 0. Now, dynamics reduces to statics. Dynamics reduces to statics means the motion brings the system to rest. Then summation over, replace this dimension of this Fi minus pi dot. Actual work done is equal to summation I equal to 1 to n Fi minus pi dot del Ri is equal to 0. This is our D'Alembert's principle.